Good morning. Welcome to our course TP 4165, Computation, Heat and Fluid Flow. Yesterday we started to derive the modified equation of the explicit upwind method. And we already started to review how far we came. So the main point is, after inserting a smooth solution into the finite difference method, we get this equation star that we derived, and that looks like we have here written again time derivative of temperature plus u times first space derivative of temperature plus delta T half times second derivative of temperature plus minus u delta x half times second derivative with respect to x of temperature plus delta T squared 6 third derivative of temperature, and then plus u delta x squared divided by 6 times the third derivative of temperature with respect to x. And that is equal to some third order terms, or error terms in delta t and delta x. Then the idea was, and the goal was, to eliminate the higher order time derivatives that do not belong to the PDE. Remember, the PDE is time derivative of the temperature plus u times space derivative of temperature is equal to 0, the linear advection equation. So we want to get rid of this in the beginning, so this coefficient, and that we can easily do by taking the time derivative of this equation and multiplying it by minus delta T half. Then the sum, we see it here, will cancel. So that we have already done. However, when we do that, we get a new term. We get, when we do this, the time derivative for this step, we get here a txt. And that is the same as t with respect to time and space, because we can interchange the derivation because the function is smooth. So, but we get this new term. So we have to get rid of that. And we can easily get rid of that by taking, by adding now u delta t half, I've already written it here, times the space derivative now of this equation. So now we do the x derivative of that. Then we get here a tx term, so that has in front exactly what we have chosen, the u delta t half. And then we get the following terms in addition. We get another, because of the derivation here with respect to x, we get a txx with a u in front. So with the u that we already have, we get the u squared delta t half. Then we don't get anything here. And we get here, we get the u delta t squared divided by 4. Here we get a 0. And here we get minus u squared delta t delta x divided by 4. So we can now proceed by doing that, and you find that in the textbook, in the edition that we have for the course, the third edition, it's on page 107, in the old edition, second edition on 105, and there you will find this table as it continues. Let us stop it here to make things a little easier. We don't get all the information, but we get already some information that will be useful for the following. So if we now do the operations that we have done, that is, we take the coefficient, that is essentially our equation that we have derived from the very beginning by inserting a smooth function, satisfying the finite difference method, this equation star. We take that, subtract this delta t half t derivative of it, and add u delta t half x derivative of it. Then we can just sum up the coefficients and we get the result. So then what is the result here? It is 1, it is u, and here that was the goal, it is 0. And here that was also the goal, that is also 0. And you see, here we get something new. Here we get the minus u delta x half and the u squared delta t half. And there we can in fact factorize the u delta x half. If we factorize that, we see here from that we get a -1, but from here we get something that is known to us. If we write here a delta x, we factorize that, we have a delta x divided by delta x. The delta x is here, and we see u delta t over delta x. So we get here a 1 minus the Courant number in here when we do the factorization. You see here, when we multiply by delta x and divide by delta x, then 1 u delta x half is here factorized, and the rest is u delta t over delta x. That is the Courant number. So that means here we get it in. And then we get here the additional terms. It is as if we would continue, then we would get them here. So in that case, if I write it here, it would be u delta t squared. Or let us be a little bit lazy here. If we have here, we have then order delta t squared, and here we have order delta t delta x. And here we have also order, we have delta x squared and also delta t delta x r times delta x. Yes.
Should it be c minus 1 instead of 1?
Correct. Thank you. Very good. Good observation. Because this is the positive and this is the minus. Correct. Good. So, but then we have received a new information here. And the new information is we know now what is the coefficient of the second derivative. Just by looking at the fluxes that we have done previously, it was only this term that showed up. It was only, I think, let's see, it was only this term here. That was the numerical diffusivity, or the numerical viscosity, u delta x half. But now we see we get also a contribution from the time discretization. And that is then responsible that we get here the C. So the result of this manipulation is that we get the modified equation. So we get, first we get the following equation from that, what we have done. We get that the time derivative of t plus u times tx, we write now this equation here, and plus, and then we have the u delta x half times c minus 1, and we just are a little lazy here. Now we say this is equal to order, say, delta squared. Might be delta x squared, delta t delta x, or delta t squared. It's on the left-hand side, but the sign doesn't matter with the order expression. So that means this will be then what we get out of this derivation. And as I mentioned in the book, it is done for even further terms. Now we write it in the form that we like. We write this on the right-hand side. And here is something missing. Important, this is the xx derivative. You see, this is just the coefficient, but it is this txx. So here is the txx sitting, and we move that to the right-hand side. So from that, and that is then what is the modified equation, just for a few terms, modified equation of the upwind method. Of the explicit upwind method. Of the explicit upwind method, and we had done it for positive u. That is then equation 14. And we have then, let me write that further here, 14. So we have the time derivative plus utx. That is the equation that we want to solve, but when we use this upwind method, we in fact solve the equation that corresponds to this. So now let me put this here away.
Can I just ask something?
Yes.
Why do you just have delta squared?
Sorry?
Why do you use just delta squared?
Because I am lazy.
Oh, okay.
If we would go to delta t to the power 3, we would also have to eliminate these terms here. So, and to save, it's essentially for saving time. So, but for getting you to the understanding, I think it's enough if we stop here. So we could do that. It's no problem. If we want to do that, just to tell you the idea, if we would want to get rid of these coefficients, we would we would add this. Let's see, I have done that. That is delta t squared over 6 minus delta t squared over 4. So that gives a minus delta t squared over 12. So then we would have to multiply to add delta t squared divided by 12 times the second derivative of this equation. If we would do that, then these three would cancel. So we could do that by continuing applying this equation. And then we would eliminate this term, this, and then we would get here a more elaborate term for that. And then we would get in the end a third order approximation with a modified equation. And in the textbook they have even done it in fourth order. So it is just a matter of applying this original equation derived by Taylor expansion more and more to get rid of all higher order derivatives. Then you can get to higher order. I just stopped here for the sake of time. Yes?
Yeah, you didn't write, or you're missing the t, or the third derivative of t with respect to t. You haven't written anything on the last line. Is that?
That is delta t squared. That is this guy here. So this is also delta t squared. So it applies to this and to this.
Okay. Yeah.
So to both of them applies. So this applies here and it applies also there.
Yeah.
So it is just second order. So we could go on, but we stop here. So then we put this on the right-hand side, and we get then u delta x half times 1 minus the current number times txx plus order, and that would be delta, if we would write it out, it would be delta x squared, delta, we take the t first, delta t, delta x, and delta x squared. So that would be then the modified equation of the explicit upwind method for u greater than 0. And that is, as I said, just to second order for the sake of saving time. But if you like, you can continue here on that, because it is, once you know how to do it for this, you can continue. But of course, if we would do it really for higher order, say up to third order, you can do it. Or even fourth order, like in the book. But if you want to do it for real high order, you should not do it with paper and pen. You should rather use a mathematical symbolic tool like Maple or Mathematica. Then you can, it's very routine operations that have to be done, and then you can do that. So the information, the new information that we get out from the modified equation is now the following. Before from the flux analysis, we only got this information. That we have a numerical viscosity of this kind. So we found only this. But now we see we can, in fact, we get something different when we take the time discretization into account. We get there this factor 1 minus c, and c is the current number. So remember, c, that was the current number, that was in our case the u delta t divided by delta x. That is the current number. So you see, we see that the size, the amount of numerical diffusivity or numerical viscosity that we get depends very much on the current number. We see also a very nice case when the current number is 1. Then this whole term is gone. We don't have any numerical viscosity, because then this will be 0. And it turns out when we would do the analysis for further terms, also those would vanish, because for current number 1, the method, the upwind method, is exact. So we get new information from this modified equation that we cannot get with the other tools. Now I would like to address the effect of these higher order terms that we in fact have when we use the upwind method. And I want to address that by looking at the effect of all higher order terms in the modified equations. So effect of higher order terms in the modified equation. So we assume now that we have the following form. We have only derived the first one, but we assume that we know also the rest. That we can express the finite difference method, then that we solve by considering the modified equation, where we in fact solve not the linear advection equation, but this with the right-hand side that contains higher order terms. And in fact, if we do it properly, these go to infinity. We have some coefficients AL, and we have L, the space derivative of the temperature. And we have determined now just the A2. We have not done more, but you could easily also get, as I mentioned, A3, but we skipped that. And in the book you find even A4. So what we do now, we make an ansatz. We assume that we have a solution of the following kind, that the solution is equal to a Fourier mode. So that resembles the Fourier analysis. We want to see what is the effect then of these higher order terms on the wave, on the Fourier wave, on the Fourier mode. And the Fourier mode is then an amplitude that is dependent on time. It is usually for a wave number k, but I skip the wave number here, times e to the I kx. So that is the ansatz that we do. So then we ask ourselves, what is the influence then of these higher order terms on the solution for the Fourier mode? So what we do then, we insert this ansatz into the modified equation. So, and then we get the following. So we insert the ansatz 16 into our modified equation 15. And then we get the following. We get here the time derivative, so that means we get only the time derivative on the amplitude, on the t hat. And we get this exponential e to the I kx is equal to, and now we get space derivatives. Each space derivative, you see here, will only have an effect here. So that will reproduce the exponential, but will give a product of k of ik. So each x derivation leads to a product of ik. Because the derivative of the exponential is ik times this exponential. So that means we can factorize ik and we can factorize the exponential. So that gives then, when we start with, I take this u already on the right hand side, we get a minus. So we get a minus u and this factor ik. And the t hat and the e to the ik I factorize out. Then we just consider the next terms. A2, we have the second derivative. Second derivative of the exponential. First derivative gives an ik. Another derivative gives another factor of ik. So we get ik squared. And that is, I squared is minus. So from that we get a minus a2 k squared. And then we get the a3 plus. We get it first plus, but then it is ik to the power 3. I squared is minus, therefore have already the minus. And we have then left ik to the power 3. And to the power 4, we again get ik to the power 4. I to the power 4 is minus 1 squared, which is plus. Therefore, I have already get a plus, a4, a to the power 4, and so on. And we get then terms of the kind al, and as we said, ik to the power l, and so on. So we get that until infinity. And now we have factorized the amplitude and the exponential, so we take that now into account. And that gives us then the t hat and the e to the I kx. Now we see we can cancel the e to the I kx on both sides. And this is just a number. It's a complex number, but it's just a number. And what we get is an ODE for the time. We get an ODE for the amplitude. And that we can solve. So the result is that we get the solution for the amplitude at any time t by the initial condition for the amplitude times the exponential with this number times t. So then we have this. This is then times e to the, and now I make a distinction between the real terms and the imaginary. The real terms and the imaginary terms. These are the real terms, and these here are the imaginary terms. So we could collect first, say, the real terms, then we have the exponential. The real terms are then the a2 k squared a4 k to the power 4 minus, and this pattern continues, and at the end it will be times t. And then we have also the complex, the imaginary part. Those are here. They are minus uik and so on. And we can see that we can factorize the ik. The ik isn't common for all of them. We have the ik here, 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 everywhere we have the ik. So then we get, and we have it also with a minus, e to the minus ik. And then we factorize the rest. And the rest is then u plus, so that is the first here, minus ik factorized, u is left. Here, ik minus ik factorized, so the k squared here is left, and it is the a4. Oh, yeah, I've forgotten something that was not so good. We can correct for that. Here I forgot the a3. So let me underline that. I forgot to write A3. So the A3 was missing here. The A3 was missing. So that we need. And here we hadn't the coefficient, here we have all the a's. So now I think it's correct. Because we need now the A3, and we argued that will then A3 and we will have a k squared. And we will continue, the next would be, if we would have the A5, would be a minus, and then that would be k to the power 4. And then we would continue with this pattern times t. So that is what we get in the end. So that will be then the solution for the amplitude. Now we can see what we have here. This term here will essentially give us something negative. And that will then give us a damping. Yes?
Is it minus 85 or plus 85?
It is, according to my understanding, minus. Because we have factorized the minus, let's see, the minus ik. Let's see, I have to think about it. Let's see, if we have the minus ik, so for this we have clear. If we have the A5, it would be, let's see, it would be, we have positive vector, it would be A5 ik to the power 5, and that would be A5 ik. I to the power 5 is I to the power 4 is plus 1, so it just gets just the I, and it is k to the power 5. But now we have written the minus in front. Minus, minus gives plus. So it's okay. Yes?
I'm not too sure like how we can get from the first line to the second.
If you have a PDE saying the time derivative is like that, the answer is that the t, that is time, that this is then t of this is hat, t hat of 0 e to the lambda t. That is the solution.
Okay.
And then I distinguished between the real and imaginary part of lambda. So the real part is here, and the imaginary part is here. So we have the lambda in our case is e to the, say, lambda real plus I lambda imaginary times t. And that is e to the lambda rt times e to the I lambda it. So that is what I did. So now let us look here. I was just arguing that this is negative in general. If we have k equals 0, it is not, then we have 0. But in most cases, then that will be, and also if we have here 0 coefficients, like we would have for current number 1, it would also be 0. But let us assume it is not, we have the general case, then this will be a damping term, because that will get the amplitude lower. So that is a damping term. Because smaller 1 in general, I asked. I've just discussed the situations when it is 0. So that is smaller 1 in general. And if it's smaller 1, this here, then it will give damping. So in our case, let us, if we would neglect these higher order terms, then if we had here the A2 and we would have a current number, say 1/2, then we would have in our case A2 would be u delta x half times 1/2. So we would get something, but it would be negative. And then we have a negative e to the negative times the time. That gives then a value smaller than 1. So that's a damping term. So that means these terms, the even terms that we have in the derivative, this comes from the second derivative, from the fourth derivative, and so on. They give a damping. And then we have here something that is inside the exponent here, and that is this expression that we have here. This expression here, that is this expression, you see this is u plus something. And that is the modified propagation velocity. It should be u, then it would be okay. But it is not. So it is a modified propagation velocity that we have here. Modified propagation velocity. Another name is phase, also we call it sometimes also phase velocity. Phase velocity. And that we could call u tilde. So, and that should be u, if it will be correct. And that is responsible for the wrong propagation of the temperature profile. That in our case, the wrong propagation of the Fourier mode. So it will be propagated with the wrong velocity. So that is then what is happening here. So we have here, and that is then responsible for this term is then responsible for the wrong speed of the propagation. That is called the dispersion error. So that leads to that's a damping term. That term leads to dispersion error or to phase error. Leads to dispersion or phase error. This term here. So we have then these two different sources of errors. One, damping. In our case, the amplitude is damping. And here, this part then leads to the wrong propagation of the Fourier mode. So we can now introduce an amplification factor. So here we went from time 0 to some time t. But if we would go just to the time delta t, we would get what is happening from one time step to the next one. So that means when we have when we go just one step, so for t equals to delta t, we get then that we can write this as the t of hat of delta t is equal to and then what we get then is the amplification factor, k delta x, if we would have that in here, and that is then to the power, it would be times the t hat of 0. So, and the g of, in this term, the g would then be what we have here. And that would be then the, say, where the g of k delta x would be then the, the delta x is implicitly in the coefficients, we can think of that. And that would be then what we get here. That would be this term here when we replace t by delta t. So then we would get e to the minus a2 k squared plus a4 k to the power 4 minus and so on times t times e to the minus ik. Now I use this u tilde that we defined before. So this, what we had here, this term here, that was the modified velocity u tilde. So we use that here, and that would be times delta t. So that would be the amplification factor from time 0 to time delta t. It would also be the amplification factor from getting from old time to the new time level. So if we're getting from Tn, this would be Tn, and this Tn plus 1, the amplification factor would be the same.
Excuse me. Why do you put delta t in one and t in the other one?
It should be delta t.
Oh,
Sorry, it should be delta t. Yes, thank you. So that was a typo. So here it should be delta t. Let me clarify that. It should be delta t. So then we have again then the same situation that we can also write then this 17. We could write that, say the t hat of t. We could then also write with this amplification factor g of k delta x to the power t divided by delta t times the t hat of 0, the initial condition. That would be another way of doing it. And the amplification factor that we have then introduced at this point, amplification factor, that is then the following. We have already seen it. That is then containing first some real part, and the real part is then this part here. And that is the absolute value of the amplification factor. So let's see. Yeah. So that is then we write it in this form, k delta x. We have seen now what it looks like, times e to the minus ik u tilde delta t. So, and from this here, we can, like we have already discussed for the general case for the solution, we can also see that for the amplification factor, where the sources of error are. So the sources of error are in the amplitude, so that is then decreased by this dissipation, by the damping term. So we have the damping term that is then the g of k delta x that we have seen is this exponential e to the minus a2 k squared plus a4 k to the power 4 minus and so on times delta t. So here. So that we have seen that is in general smaller than 1 for k not equal to 0, and we should also add for c not equal to 1 in our case. And that leads then to the dissipation error. So that is one source. And the other source is then coming from the wrong propagation speed. That is also showing up in the amplification factor, so that we have a wrong phase velocity that is the u tilde instead of the correct velocity would be u. And that leads to the dispersion error. Leads to a dispersion error. So then we see here the two different sources of errors in this analysis for just one Fourier node. So we can look at examples for that. Let's see. You can do that also in exercise 3 that is to come. So I take an example from last year's course. So that is for the finite difference method, but we would get the same thing if we have periodic boundary conditions, also if we would use the finite volume method. So let's see. So that is the initial condition, so you see it is just a simple sign, and we let that now propagate. You see only very few points. And the current number here is 1/2. So and that is the result after, I think, time 2. So what has happened here is typical for the dissipation error. The amplitude that should be like this is the exact solution, has not been met. The amplitude has been reduced by the numerical dissipation. So the amplitude is now here. So instead of having amplitude 1, we have here amplitude less than 0.4. And if we would continue that further, it would approach 0. So that is an example of the dissipation error for reducing the amplitude of a wave. Let's look at an example with a discontinuity. Here you see I've also checked the error there. You'll do that also now for your for exercise 2. So now we look for a discontinuity. So let us first enlarge that and explain the initial condition. So we have here discontinuity, which is sitting actually between 0.2 and this grid point, because here this last grid point that has 0, and the next grid point at 0.2 has 1. And that is 1 until 0.4, and the next grid point has the value 0. So there we have a discontinuity. The rest is 0. So now we can see what happens when this is propagating. Again, with the current number is 1/2. And you see that this continuity here is smeared. So instead of having here a sharp discontinuity, in fact it should be a straight line between 0.6 and the next grid point, but this is just a plotting issue that we have this linear connection of the points. So instead of having a discontinuity, this gets smeared, as if we had a viscous flow. The same on the other side, and we see also the amplitude here is also starting to decrease. So we cannot maintain the correct value here. And these are effects of dissipation. This is numerical dissipation. And that is the disadvantage of this method. So if we would change it, let's see if I find that. That was the discontinuity. Let's see the upward discontinuity. This one here. I open it now and I change the current number. So I call it here CFL. So here it was 0.2, I change it to 1. So I save it, and then I run it. What should we expect for current number 1?
Exact solution.
Exactly. We should expect the exact solution. And you can show that in exercise 3 to come, that is true, and we can just see if it is also true when we run it. Let's see. So we enlarge, and then we let it go. Yes. We get exactly the solution that we should get. So that is a beautiful property of the Upland method, that it is exact. So if you have a chance then for problems where we don't have constant coefficients, you cannot get the current number 1. But when you have a problem, so here we can get the current number 1, because it's the coefficient u is constant. But when the coefficient is varying, we can try to choose the current number as close to 1 as possible. Because somewhere in the flow we have a large velocity, then we choose the current number according to that equal to 1. When the velocity is lower, the current number will be lower, and then we will have some dissipation effect. So that is then what the dissipation error that I wanted to show you. And just I want to get that back to the old value. So, and then let's see, I have also an example for the, let's see, for dispersion error. Let's see, I have to go in here, open that. Let's see. So tick-tock is, by the way, measuring the time that is occurring between these two occasions when the program is run. So then we put that here. So that is now solving here. Actually, it's a 4th order method that is used, so let us enlarge that to see what's going on. So here a Gauss pulse is propagated. So the blue one is the exact solution, the green one is the numerical solution. And these oscillations here are due to the wrong propagation of the waves with the higher wave numbers. So they are not correctly transported. This is the error. So that is an effect of dispersion. So all waves should be transported with the same velocity, with the true velocity, and the higher wave numbers are. But the smaller wave numbers are correctly transported. That is the long waves. They are transported correctly, but the small waves with the small oscillations, they are not transported correctly, and then we get such effect. That is an example of the dispersion error. If we would have just one sine wave, then we would see that the sine wave might be here, but if we have not a good resolution, so that then the wave number, the computed wave number would be behind. That would be transported with a too slow velocity. But when here in this example, in the Gauss pulse, we have many Fourier modes in it, and the waves with the low wave numbers are transported correctly, but the waves with the high wave numbers, with the high oscillatory movement, they are transported too slowly. So that is an example for the dispersion error, and it would be even worse if we had a 2nd order method. This was the 4th order method, which is even more accurate. Okay, so we stop here and take 15 minutes break.